Hello everyone, I'm Hyunjun Lee from Korea University. Thanks for coming to listening my presentation today. Before I begin, I would like to acknowledge the help of my co-authors. I would like to thank my advisor Professor Sangbin Lee, Gibong Lee, and Dr. Stun and my colleagues for their support. Today we are going to present the new concept of inverter embedded insulation testing for preventing PD-induced failure of low-voltage machines. The stator winding insulation failure is one of the major failure mechanisms of electric machines. The thermal, electrical, mechanical, and environmental stresses could degrade the machine insulation. As the number of motors operated with inverters, the high DVDT voltage introduces additional thermal and electrical operating stresses. The high DVDT results in the voltage overshoot at the terminals and cause uneven distribution of voltage, which could produce partial discharge in turn, phase, and ground-wire insulation of low-voltage motors. Since low-voltage motors' organic insulation material is not PD resistant, the winding will fail within a short period of time. The recent trends in traction drive system is, first, transition from random wound hairpin winding design to accomplish higher slot fill factor and automated manufacturing process. Second, transition from silicon IGBT devices to wide bandgap fast switching devices such as silicon carbide and gallium nitride to achieve high efficiency. Third, and increase their DC link voltage to improve entire system performances. The new type of stator design could suffer from PD since they have a maximum voltage between N-turn coils, and the fast switching and high DC bus voltage will increase the high DVDT stresses. In addition, the motor for electric propulsion system can be operated at high altitude, where PDIV is significantly lower. It will make PD-induced stator insulation failure more likely to occur and is expected to become a serious problem in the future. The objective of this work is to develop a new concept of inverter-embedded PD testing for preventing PD-induced insulation failure of low-voltage machines. The proposed strategy is to use the inverter for impulse PD testing at the motor standstill. It will be shown that the proposed method provides reliable, low-cost PD testing by testing motor at voltage level higher than the operating voltage for early detection of insulation aging without expensive PD sensors. The qualification of low-voltage motors driven by VFDs, a standard offline PD test method under impulse excitation, have recently been suggested. The IEC standard 60034-18-41 guarantees that the motor will be free of PD under the worst-case stresses. Considering that the low-voltage motor insulation is not PD resistant, there should not be any PD activity in the turn, phase, or ground-wire insulation under the worst-case operating environments. The impulse PD test is usually performed with a commercial surge tester. The waveform below shows the impulse voltage and PD pulses captured by UHF radio antenna with oscilloscope. However, even if the motor is qualified for PD-free operation in the design or manufacturing stage, the PDIV decreases due to the operating stresses. This is the problem. PD testing is performed only after manufacturing and cannot detect insulation degradation. Thus, inverter operation can eventually rise to PD that leads to stator insulation failure. The concept of proposed strategy is to use the inverter to perform impulse PD testing whenever the motor is stopped. If the offline PD test I explained earlier can be performed regularly, it is possible to warn the user of PD activity. Plus, PD test at voltage higher than the operating voltage, it will give an information of decreasing PDIV. Therefore, it is possible to give an early warning of insulation degradation. So, there are two possible means of increasing impulse voltage. The first one is increase the voltage overshoot by fast turn-on of switching devices. And the second one is to increase the DC link voltage. The first method, increase in voltage overshoot. With the low gate resistance value, switching devices turn on and off speed can be decreased, as shown below. The value of RG can be adjusted with minor modifications to the gate driver circuit or with inactive gate drivers. It's not complex, but still needs a gate board circuit modification. The second method is increasing the DC link voltage itself. The conventional three-phase rectified inverter circuit below is modified to boost its input voltage. The DC reactor and braking chopper could be used as a boost converter and can boost the DC link voltage. It is just a simple example, and there are some other topologies that doesn't require circuit modifications, for example, back-to-back converter for wind turbines and so on. The thing good about this method is that it can measure the PDIV, thus gives a quantitative information about insulation. However, its modification is relatively complex than the previous slides. To detect high-frequency, low-amplitude PD signal, high-frequency antennas are the lowest cost option. The high-pass filter is used to remove low-frequency noise from PD signals, and the output of the high-pass filter is fed into a RF log amplifier for broadband amplification of the small signal. The amplified signal is then compared to the PDA reference voltage with the ultra-fast comparator. If the rising edge of the comparator's output signal is captured, the MCU will acknowledge the PD activity. The proposed method was tested on a 5 horsepower, 380 volts rated voltage induction motors with inverter stack have 1200 volts rated IGBTs and 800 volts DC link voltage. Since it is hard to find the stator winding that produces PD above 800 volts and below the test voltage, a twisted pair of conductor was used as a PD source. The twisted pair was carefully adjusted to emulate the case where PDIV level has decreased to approximately between 920 volts and 950 volts as shown below. And two types of monopole antennas were tested for detection of PD. A commercial coaxial cable antennas with 1 cm of conductor exposed were placed outside on the motor frame and inside the motor. Also, commercial radio antenna with passband between 70 and 1000 MHz was placed outside the motor. The signals from 3 antennas were measured and processed for comparative evaluation of PD detection capability at different locations. All antenna measurements were high-pass filtered before processing with the PD detection circuits. For the case where VDC is 800 volts and RG is set to 15 ohm during turn-on, 5 impulses have been applied at 100 microseconds intervals for testing. It is only necessary to apply a small number of short-duration pulses, thus can minimize the testing stresses. The two methods for increasing the impulse voltage were tested independently. For fast turn-on operation, the gate resistance of high-side switches changed from 33 to 12 ohms. And for the DC link voltage boosting, DC input reactor and braking chopper is reconfigured to boost DC link voltage from 800 to 900 volts. There is no PD activity detected by any sensor under the rated DC link voltage of 800 volts and nominal gate resistance of 33 ohms. This indicates that the motor will be free of PD under normal stresses, and therefore the decreasing PDIV cannot be detected with the online monitoring methods. If the value of RG is decreased from 33 to 12 ohm without increasing VDC, the peak impulse voltage was 1004 volts for this case, and PD activity could be observed with all 3 antennas. The peak impulse voltage was 954 volts when the DC link voltage was temporarily increased to 900 volts. For this case, PD activity could be observed with all 3 sensors. For both cases, PD could be detected with higher sensitivity with radio antenna and internal coaxial cable. The sensitivity of the internal antenna is higher than that of external because the PD signal is attenuated by the frame of the motor due to the Faraday shielding. Considering the size of radio antenna or other options, installing the coaxial cable antenna inside the motor frame would be a viable and low-cost option. And finally, here's an experimental result of PD detection circuits. The upper red waveform is high-pass filtered PD signal. The blue RF log amplifier output signal is compared to the black threshold level using the fast comparator. Then, MCU acknowledges the PD activity, generates the PD detection signals. To conclude, a new concept of using the inverter to perform the impulse PD test at motor standstill has been proposed and verified experimentally. The main concept is to perform the test with the peak impulse voltage temporarily increased above the operating voltage to monitor the decrease in PDIV at an early stage. The results confirm that the proposed method can be used to detect a decreasing PDIV due to the insulation degradation. It was also shown that PD can be detected with a low-cost monopole coaxial cable antenna installed inside the motor. Since the proposed method is capable of performing the impulse PD test automatically under voltage stress higher than that during motor operation, it is expected to detect insulation aging at an early stage to improve the reliability of the motor. And I would like to finish by thanking you all for your attention. Again, thank you very much.